when you're at 0 over the length of the well, the solution is e to the I cx. But here's the kicker. The solution outside of this area is 0 because of the infinite potential. I mean, imagine if there were infinite walls of force holding you back. What would even be the probability of you getting past those infinite walls of force? 0, right? So that explains why the wave function is 0. But the free particle is what happens when we take the width of the infinite square well and extend it to infinity. Now, that means the entire wave function is always e to the I cx. It's allowed to just flap free, and that is not a good thing. Why? Because if you take the integral of the modulus squared, well, what's the modulus of this? That's better written as the function times its conjugate, and the conjugate of ICX is just negative ICX. And, oh, hold up, wait a minute. Since we're integrating over the entire real line to find the normalization constant that we have to multiply this by to make a viable solution, well, what happens when we do this? It becomes minus infinity to infinity. Well, this becomes a constant, 1, and if there's an amplitude, it becomes a squared, which becomes, wait a minute, 1 times infinity minus negative infinity? How does that even make sense? Well, at the end of the day, what infinity minus infinity to infinity means is the limit as b approaches infinity for some b of the integral from minus b to b of 1 dx. So the integral of 1 dx from minus b to b is b minus b, which is just 2b. And the limit as b approaches infinity of 2b diverges. Hey, wait a second. That means the quantum free particle doesn't exist. There is no such thing as a free particle in quantum mechanics. Well, at least that's what we think so far. Sure, the wave function is non-normalizable, but does that mean that this is useless? Well, actually, as we'll come to see, no, because every single viable solution will actually